Welcome everybody to the fourth and last video with the solution to the first project Euler problem. In the first video I created a trivial solution, and in video 2 and 3 I tried to make the Python program faster by avoiding divisions, but I ended up making them slower instead. In this video I will go for the math approach, derive a formula which should give us a very fast program. So maybe the way to go is doing math. Basically we have these numbers. So let's take the fourth version. Let's copy this. As we discovered in video part 2, the pattern of numbers is repetitive, starting over every 15 numbers. If you look at each block of 15 numbers at a time and sum them, you get another pattern. The first block of numbers sums to 60, the next to 165, the third to 270, each block being 105 larger than the one before it. A series of such numbers is called an arithmetic series, and there is a simple formula for how to add them up. The total iterations would be the maximum number, and I'm using 1 million now because we're using 1 million divided by 15. This is integer division, so we get a smaller integer. So basically we'll have that number of full iterations. Let's call it total full iterations. So the sum will then be... So let me cut in. Rather than showing the whole process of deriving the formula, I'll summarize it. The sum of an arithmetic series can be calculated with this formula. You sum the first and the last number, divide by 2, basically getting the average of all the numbers, and multiply with the number of numbers. In our case, we have just calculated the number of blocks, and we know the sum of the first block, 60. And then we can calculate the value of the last block, since we know that they increase by 105 every iteration. I didn't use that one, or that one, or that one, or I. So, looking kind of good, except it's wrong. So let's run it with something much smaller, where we can verify this is doing the right thing. Let's say that we're running it all the way up to 20, and then let's make that upper limit 20 and use that instead of that constant. Okay, so let's see if we can do this. And that was also upper limit, right? So it should have been 78. Now it's smaller, not bigger. Interesting. Let's say 5. That should be 3, right? 0. 15. So 15 should have given us 1 full iteration. Actually, that should be upper limit minus 1, right? So the iterations are too small, are they? So what is the math here? 8, 14, 60. So that's 60. Is it... Wait! Did I divide too much? That should be divided by 2, right? I suspect it's still wrong, right? That's too high. No, it's not too high, it's far behind. Was the other one also far behind? It is far behind. So maybe it's that part and fixing the end of this as well. Let's see, we can do a loop here, right? Last number upper limit times total full iterations for range last number plus 1 to upper limit, and let's do it the simple way. Huh, still wrong. It didn't do anything. Why didn't it do anything? Don't you have 1,000? How can that be 66,000? Oh! Not upper limit. 15. 15. Look, right. It's correct. And if I change the upper limits now to 1 million, or was it 10 million? 10 million. Let's say 10 million. It takes a while. For the first one, it took 1.5 seconds for that. Next one, 1.7 seconds. Third one took 2.8 seconds, and the math part took 0. So basically, by doing math, it took us way longer to program, but we got a much faster program. So, some simple programming, just doing the first problem in Project Euler, and we can set it to the default. So, was it worth investing all that time into making a smarter version? Doubtful. Was it fun? Yeah, it was. So, see you next time, maybe for problem 2 in Project Euler.